Hello everyone, my name is Esther.
And I'm Elaine. Welcome to our presentation for the M3 Practice Hackathon.
In this video, we are going to walk you through our machine learning workflow for predicting medical insurance charges. Our discussion today is strictly guided by the two main prompts required for this assignment. First, what specific steps did we take to improve the performance of our regressor? And second, what did we do to assess and improve the fit of our model?
Exactly. We built our solution in a Colab notebook using Python and scikit-learning. Rather than just relying on a basic model, we took a very intentional approach to data preprocessing, feature engineering, and validation. Let's dive right into the first prompt. Esther, how did we go about improving the raw performance of our regressor?
So to improve performance, we realized that the most important work happens before the model even sees the data. We started by analyzing our target variable, the insurance charges. If you look at the histogram on the left, you can see the raw charges are heavily right skewed. Most people have relatively low medical costs, but a small group has massive expenses. Machine learning models struggle with extreme skewness. So to improve performance, we wrapped our model in a transformed target regressor, applying a log 1p transformation. You can see the result on the right, a much more normal distribution. This conceptual shift directly minimized our mean squared error.
That's right. The next massive leap in performance came from feature engineering. So we didn't just pass the standard columns to the model. We thought about the domain. For example, the smoker column was messy, containing values like yes or single Y, untrue, and 1. We wrote a custom Python function to safely map all these variations into a clean binary format.
Also, beyond cleaning, we created interaction features. From domain knowledge, we know that smoking is bad for your health and a high BMI is bad for your health. But if you have a high BMI and you are a smoker, your medical costs don't just add up, they multiply.
To capture this, we engineered three specific interaction features: BMI smoker, age smoker, and BMI age interact. We initially also experimented with binding age into life stages like 0, 10s, 20s, and so on, but later we find it doesn't make sense. So we just replace it with polynomial features such as age squared and BMI squared to better capture nonlinear effects while keeping the variables continuous. By explicitly feeding these interactions and nonlinear beings into our pipeline, we made it much easier for our tree-based models to discover these complex relationships.
Once our features were engineered, we set up a robust pre-processing pipeline using a column transformer. For numerical features, we used a simple imputer with a medium strategy. We chose medium over mean because it is much more resistant to outliers in features like BMI or age.
So to categorical features, we imputed missing value with the most frequent value, followed by a one-hot encoder.
Now, an important procedural note here. You might notice we completely skipped feature scaling, like standard scalar. This was a deliberate choice. We selected XGBoost and Random Forest as our primary regressors because these are tree-based models that make decisions by splitting nodes at specific thresholds. They're completely insensitive to the scale of the features. Skipping scaling keeps our pipeline simpler and faster without sacrificing any performance.
Speaking of models, we structured our code to default to attributes. Attributes is an advanced ensemble method that builds trees sequentially, where each new tree tries to correct the residual errors of the previous ones. This gradient boosting approach is fundamentally designed to yield higher performance than standard models. We also called a fallback to a random forest regressor just in case the attributes library wasn't available in the environment, ensuring our code is reliable.
So that covers performance. Now let's transition to the second prompt. What did we do to assess and prove out the fit of our regressor? It's easy to get a model to memorize the training data, but assessing how it generalizes is the real challenge.
To assess the baseline fit, we entirely avoided a simple single train test split. Instead, we used a five-fold cross-validation strategy. By partitioning the data into 5 distinct folds, training on 4 and also testing on 1, we obtained an average mean squared error that is much more representative of how the model will perform on unseen Kaggle test data.
But our most powerful diagnostic tool for assessing model fit was the learning curve. We plotted the training MSE and the validation MSE on the y-axis against the fraction of training data used on the x-axis. This visual allowed us to directly diagnose the bias-variance trade-off.
Exactly. Actually, when assessing the fit, we looked at the gap between the two curves. So if the training error is super low, but the validation error is also very high, that means the model is overfitting. So it has a high variance. But if both errors remain high and close together, it's also like the underfitting. So it means a high bias. So by analyzing this curve, we could clearly see the trajectory of our model's learning capacity as we feed it more data.
So finally, once we assess the fit, how do we improve it? Our main strategy for improving the fit and preventing overfitting was hyperparameter tuning using randomized search CV.
All right, and in this section, you can see we actually conducted numerous tests using different parameters. So we didn't just let the attributes grow infinitely deep trees. We explicitly tuned parameters that act as regularization. For example, we tested max dips value of 3, 4, 5, 6, and 7 to restrict how complex each tree could get.
We also tuned subsample and co-sample by tree, setting them to fractions like 0.7, 0.8, 0.9, also 0.6. This means each tree in the ensemble is trained on a random 70% or 80% or whatever subset of the rows and columns. This injection of randomness prevents the model from relying too heavily on any single feature or memorizing noise, which directly improves the generalization fit of the model.
So to wrap up, we didn't just treat this as a plug and play exercise. We improved performance by transforming our skewed target, engineering domain-specific interaction features, and also utilizing XGBoost.
And we rigorously assessed and improved the fit of that model by employing five-fold cross-validation, diagnosing bias and variance with learning curves, and applying regularization through randomized hyperparameter tuning.
That brings us to the end of our workflow discussion. Thank you very much for listening.
Thank you.